Well, hi there. Welcome to Itasca Water's Practical Water Wisdom series. I'm Brian Whittemore, your host for today. Today's program is called PFAS, commonly called forever chemicals, in water. How did they get there and why are they so challenging to address? First, let me tell you a little about Itasca Waters. We're a local nonprofit headquartered in Grand Rapids, Minnesota, with members who either live or vacation in our area. Our goal is to continue to find interesting ways to educate residents in Itasca County about how to keep our water clean for both the environment and the economy. We've been teaming up with like-minded people and organizations for 16 years. You can read about those projects on our website at itascawaters.org. If you have an interest, please consider joining us and becoming a member or a volunteer to help support programs like this. We thank our partners, shown here on your screen, for their support in producing this program. Today's program will work as usual. Our guests will speak for about 30 minutes, and then we'll answer questions directly from you. To submit a question, you only need to click on the Q&A button at the bottom of the screen and type in a brief question. And you can do this at any time, and we will read the questions on your behalf. We will not be using the chat function. This program is being recorded and will be available for viewing online through our website at itascawaters.org. Also, we value your opinion, so please click on the survey link, which will be on screen at the end of today's program, or complete the survey that will be sent to you by email, and we thank you for doing that. Now on to today's program. Dr. Bridget Ulrich grew up on the Iron Range in Virginia, Minnesota. Prior to joining NRRI, she worked as a postdoctoral researcher at the Swiss Federal Institute for Aquatic Science and Technology in Zurich, Switzerland. She is currently a principal research scientist and leads a research team focused on environmental chemistry. Her team specializes in the application of advanced analytical techniques to track contaminants in the environment, as well as the development of water treatment solutions to prevent pollution at the source. Bridget, it's all yours.
Thank you, Brian, and thank you everybody who has been able to join us for today. I'm really excited to connect with this community and talk about a topic that I really care about, which is PFAS in water. And for those of you at home, momentarily, I believe a link will be added to the chat where you'll be able to access a PDF of the presentation and follow through some links to different resources that I've included. Or you can also scan this QR code to access the PDF of the slides. So with that, I'll advance the slide. Okay, so you may have heard of PFAS and seeing it all over the news lately, and potentially that has you feeling concerned, confused, or curious about why these chemicals that have been in our households for decades seemingly are all of a sudden receiving so much attention. But first, to just get this straight, not all chemicals are inherently hazardous, and everything is made up of chemicals, including the water we drink, the air we breathe, and our bodies. So the issue is that some chemicals can be more harmful than others. So from this webinar today, I'm hoping that you can take away a better understanding of what PFAS are, why they've caused so much recent concern, how they've become so widespread in the environment, and what is being done, and if there's anything else that we can do. So to get started, PFAS practically are a class of organic compounds that were first developed in the 1940s and 50s, and they are now widely used in various household products today, in part due to their useful non-stick properties. Technically, according to the EPA, PFAS are chemicals that have at least two adjacent carbon atoms, that one being a fully fluorinated carbon atom. So I'm showing you some structures here, and I'll use some basic chemistry today to describe PFAS to you. But In these structures, the locations of the carbons are indicated in blue. Carbon is so common in organic molecules that chemists tend to not even show the C, so they're just shown as a linkage. And the F is the fluorine. So you see that it's fully fluorinated when the carbon is bound only to a fluorine and it can't bind to anything else. So these two compounds, PFOS and PFOA, or PFOS and PFOA, might be the two PFAS that you've heard the most about. However, they are not the only PFAS, and there are actually thousands of PFAS that exist. So I'm going to touch more as we go about what PFAS are, but for now I'll move on to talk about why they've caused so much recent concern. So as I said, some chemicals are more harmful than others. Being toxic is definitely one thing that makes the chemical harmful. However, it's only harmful if it's toxic and you're also exposed to it at a level that it can cause a hazard. So the more obvious type of toxicity that might come to mind is acute toxicity. And this would be a short-term exposure at a high concentration where you would quickly experience the effects, and it's very likely that they will occur. And while PFAS are acutely toxic, the vast majority of us are not exposed to PFAS at a level where they are acutely toxic. And when we're thinking about PFAS, oftentimes chronic toxicity is what is more of a concern. So this is when you have long-term exposures at lower concentrations, and in this case, your effects could emerge over years or decades, and it's a lower probability that the effects might occur. So it becomes more challenging to understand if that particular exposure actually led to that effect. So I said just because you're exposed to a toxic chemical doesn't necessarily mean that it's going to have a toxic effect. So for most chemicals, there is a so-called no effect range where you can be exposed to a certain dose or intake, and there's no expected risk of an effect emerging. And for practical purposes, we can call this the safe range. And then once a certain threshold is passed, there can be an increasing chance of effect. So we can be exposed at low or high levels, and if you are infrequently exposed at low levels, your long-term intake will be lower than if you're frequently exposed at low levels. So this is where the concern for PFAS can come in if we are routinely exposed at very low levels. And lower levels of exposure can be more harmful to more vulnerable, smaller bodies because the PFAS or other types of chemicals can amount to a higher concentration within their bodies. So you may have heard in the news that the US EPA recently set national drinking water standards for PFAS. And they set what we call the maximum contaminant level goal, or which is essentially the level where the EPA could be confident that there's not a risk of an effect of 0 parts per trillion, which I can see might be confusing for many people. What does that even mean? So 1 part per trillion, to put things into perspective, is a very, very small concentration, and that would be equivalent to approximately 1 drop of water in 20 Olympic-sized swimming pools. So 0 parts per trillion, for me, as an analytical chemist, doesn't actually exist. So we measure contaminants based on a known method detection limit, which is essentially the threshold at which we can actually see a contaminant with our detection methodologies. So what this 0 means is that the EPA was not able to establish a safe effect range for PFAS in drinking water. Part of the reason for this may be that PFAS don't show typical dose-response relationships, which made the science difficult to interpret. So in the end, we also have enforceable levels, which are levels of different contaminants that are actually able to be measured. So they settled on enforceable levels of PFOS and PFOA of 4 parts per trillion in drinking water. So in addition to the Safe Drinking Water Act, the US EPA can also regulate chemicals through the Toxic Substances Control Act, or TSCA, to regulate production of chemicals that have been found to be persistent, bioaccumulative, and toxic, or PBT chemicals for short. And I'll get more into each of these aspects throughout the talk, but basically if they're persistent, they don't degrade and they remain in the environment. If they're bioaccumulative, they accumulate in organisms and in people over time. We just discussed that toxicity means that exposure is associated with certain health effects. But there are also other aspects and properties of chemicals that can make them more harmful in terms of making you more likely to be exposed to them, including being ubiquitous or present everywhere, as well as mobile, so their ability to spread throughout the environment once released. So here I'm highlighting some research from a recent survey of persistent bioaccumulative and toxic contaminants in sediments in Lake Superior. And I'm showing several classes of contaminants that have been phased out under the Toxic Substances Control Act, starting from the 1970s. So for example, you can see that DDT, or at least its degradation product DDE, PCBs, and dioxins were all phased out in the 1970s to 80s, and you can see that their concentrations in sediments have been decreasing since that time. PBDEs were phased out more recently, and their concentrations in sediments are still starting to level off. So for PFAS, here I'm showing in the teal and the red, PFOS and PFOA. You can see that their levels in sediments have leveled off somewhat since their production was phased out in the US in approximately 2015. However, this yellow line here is the total PFAS. So that's the sum of the 30-some PFAS that we measured in the sediments. And you can see that even though PFOS and PFOA have leveled off, the total PFAS are continuing to increase because there have been various other PFAS that have emerged to replace PFOS and PFOA once they were phased out of production. So one of the things that makes PFAS especially unique among persistent contaminants is that they are especially persistent. So I'm showing here the chemist's best friend, the periodic table. And if you look over to the column in purple called the halogens, all of these persistent contaminants have one of those halogens, but with fluorine being at the top of that column. So this essentially means that the carbon-fluorine bond is one of the strongest bonds in organic chemistry, which is why they're so persistent and so challenging to break down. And the term forever chemicals arose because fully fluorinated PFAS do not fully degrade in the natural environment. PFAS are also bioaccumulative. So they can be present in our bodies for many years once we're exposed to them. So most PFAS have half-lives in human bodies that range from 2 to 30 years, which means that for a single exposure to a certain type of PFAS, it would take approximately 2 to 30 years for your body to remove half of the amount from that exposure. PFAS also are bioaccumulative in fish, and if humans eat fish that have been exposed to PFAS, they can expose themselves to a higher dose from consuming that fish. And that is why we have several fish consumption advisories in Minnesota. Of relevance to northern Minnesota, I'll point out that there are current fish consumption advisories for Fish Lake and Rice Lake near Duluth, or PFOS. So I'm going to talk a little bit more about structure just to give you some context. The PFAS bioaccumulation potential depends on the PFAS chain length. So you can see that as the number of carbons decreases, the length of that carbon-fluorine chain is also decreasing. And you might recognize some of these acronyms that I'm showing you here for the various different types of PFAS depending on their chain length. And it also depends on the so-called head group. So you can see here in these two circles that the group at the end of this chain is different. And these are called the sulfonates with the S, or the carboxylates with the carbon. And typically the sulfonate PFAS are more bioaccumulative than the carboxylate PFAS for a given chain length. So these structural details are important to understand why PFAS are so complex and how they are challenging to understand how they move through the environment. So I already introduced the idea of toxicity, and now we'll start to talk about it in relation to PFAS, with a disclaimer that I am not an epidemiologist, but I will explain to you what I understand about the science and direct you to some resources. So, as I said, just because you're exposed to a chemical that is toxic doesn't mean that there's necessarily going to be an effect. And since it is clearly unethical to conduct a controlled study and to expose humans to a substance that may be harmful, scientists need to try to understand the potential effects of these chemicals based on populations that have already been exposed unintentionally. And they do this by looking at exposure levels, generally levels of PFAS in blood or serum versus the occurrence of effects in populations. And so just because they establish a correlation, it doesn't always necessarily mean correlation itself doesn't mean that the PFAS or other chemicals caused that effect, because there are other potential exposures or coexisting environmental factors that might also be correlated to PFAS levels that also could have caused that effect. So many of these studies, they've established correlations, but haven't necessarily established causations. So that doesn't mean that PFAS don't cause these effects. It just means that we haven't, been able to produce the definitive evidence that PFAS indeed cause these effects. So many of these recommendations for health effects stem from the observation of correlations between exposure effects among communities that have brought the US EPA and other entities to the conclusion that there is some risk of exposure to PFAS that may lead to health effects at some levels. And you can follow this link to the US EPA website. But an example of some of those effects that have been correlated with PFAS exposure include reproductive effects, developmental effects, cancers, immune function, endocrine disruption, and increased cholesterol and risk of obesity. And to further complicate matters, as I mentioned, PFAS are more than just PFOS and PFOA, and approximately 15,000 different types of PFAS are known or suspected to exist in the environment. And most of these compounds have unknown toxicity. So many of these compounds are so-called polyfluorinated PFAS, so PFAS that have part of their molecule that is fully fluorinated, but another part that is not. And these compounds can be called precursors because they can break down in the environment, but then they just form these fully fluorinated PFAS that cannot break down further. So to conclude this section, PFAS have caused a lot of recent concern because they are persistent, bioaccumulative, and potentially toxic, having been linked with potential health effects. However, they are particularly persistent. So next, I'll talk a little bit about how PFAS have become so widespread in the environment. So PFAS have been detected all around the world, even in remote areas not near a known source. They're also ubiquitous in our household products, and even though PFOS and PFOA are no longer produced in the US, they can be present in products from outside of the country, and there are also many other different types of PFAS that can be present in different products. And because of that, PFAS exposure is essentially unavoidable. However, most people are exposed only at very low concentrations. So PFAS can enter the environment from the products that we use in our households through our wastewater, so through our showers, toilet, or laundry. If you're washing waterproof clothes, for example, that have a coating containing PFAS, and also through landfills. And even if the water that leaches from landfills and that leaves your sinks and toilets goes to the municipal wastewater plant, These plants are not designed to remove PFAS, and it turns out they're not particularly effective at it. However, PFAS in wastewater are very diluted and at very low concentrations, and are generally, it's considered to be a less urgent source of contamination in the environment relative to some other known high concentration sources. For example, various industries use PFAS in their production processes and have high concentrations of PFAS in their wastewater. And then one other source that I want to highlight today are aqueous film forming foams. So these are firefighting foams that are used to extinguish fuel fires that historically were used for firefighting training purposes, oftentimes at military sites. And in that process, that high concentrations of PFAS containing fluids were released directly into the ground. And over the years, that means they can enter groundwater and move through groundwater, which has caused quite a concern. And in addition to the high concentration, this contamination is also very widespread. So the Department of Defense has identified over 700 sites across the US that need to be further assessed to understand the potential aspects of PFAS contamination that may need to be addressed. And I'll highlight right here, you see we do even have our own DOT in northern Minnesota that is from the International Guard site at the Duluth Airport. And we also have a site at the Lake Superior College Emergency Training Response Center where AFFF was known to be used for training activities. So once PFAS enter the environment, how do they spread through it? So they can enter watersheds either through runoff from contaminated sites, direct discharge of wastewaters, or from spread in groundwater from contaminated sites that leaches into streams. And once they enter waterways, they're able to spread more quickly regionally through watersheds. And eventually discharge to lakes, for example, Lake Superior. And in large lakes like Lake Superior, they also can potentially be transported throughout the lake in currents and by attachment to sediments and resuspension of sediments over time. Another way that PFAS can be transported in the environment is through the atmosphere. So this allows them to be transported long distances and has enabled them to be able to be present in very remote areas that are seemingly nowhere near an emission source. So here I'm highlighting some more results from our recent sediment survey of Lake Superior, and these dots represent concentrations of total PFAS, so the sum of 37 different PFAS measured in surface sediments in Lake Superior. And the larger dots mean higher concentrations. So the immediate thing to point out is that we found detectable levels of PFAS in sediments at all sampling sites. So even in Lake Superior, which is widely considered the most pristine of the Great Lakes, PFAS are still ubiquitous and widespread. Another aspect of PFAS that makes them very unique is that they're very mobile in groundwater. So typically contaminants that are bioaccumulative also tend to stick strongly to soils, which would make them less mobile in groundwater. So for example, PCBs. However, PFAS they seem to have a bit of a dual personality, and as surfactants, they are both bioaccumulative and mobile in groundwater. So the hydrophobic tail that I mentioned earlier, the carbon-fluorine chain, tends to want to stick to soils. It doesn't prefer water. However, this head group is typically charged in the environment, which makes it want to strongly associate with water. So these compounds tend to accumulate at interfaces, and these aspects make them have the ability to move more quickly in groundwater than other highly bioaccumulative contaminants. So PFAS can spread through groundwater and lead to contaminated drinking water. And this is an issue that the East Metro is facing right now. And there was recently a settlement with 3M where the state of Minnesota will receive $720 million to be invested in drinking water and natural resource projects in the Twin Cities metro area to address PFAS contamination. So I understand if that makes your head explode a little bit, that it's going to cost $720 million to address some of these issues just in the East Metro. And that really goes to demonstrate that once PFAS enter the environment, they're extremely challenging to address and how we need to prevent them from entering the environment in the first place. It also goes to show that treatment is expensive, and I'll also touch a little bit on that in a bit. So that concludes that PFAS have become very widespread in the environment because they are ubiquitous in various products, and they also are very mobile in the environment once they are released. So now, to end on a more positive note, I can talk about what is being done and what else we can do to address this problem. So I'm showing here an infographic from a team at the University of St. Thomas and Barr, where they evaluated the cost to treat PFAS at the rate that PFAS are currently being released into the environment. And what they found is that there's not enough money in the world to remove PFAS from the environment as fast as we are adding it. So that means that the amount of money estimated to treat all the PFAS that are currently being released into the environment exceeds the global GDP. So what needs to be done? Essentially, we need to start releasing less PFAS into the environment. So what can agencies do to help this? So first and foremost, we do need to address contaminated drinking water sources to prevent communities from being exposed to PFAS through their drinking water. And there have been new resources available as a result of the EPA's recent national drinking water regulation. And these links will bring you to some examples of grants that are available for small communities to have their drinking water tested, and also a technical assistance program. We also need to eliminate the non-essential uses of PFAS in the effort to reduce their release to the environment. So this could involve encouraging replacements in consumer products and also improving transparency in supply chains. We also need to, again, prevent PFAS from entering the environment in the first place. So for known and essential uses for PFAS, we need to find a way to prevent them from being released and to treat them at the source. And then finally, for existing contaminated sites, we need to figure out how we need to put in the effort to prevent the pollution from spreading further. So first of all, what has been done to regulate and replace PFAS already at the state level? You may have heard that Minnesota recently passed a PFAS ban in consumer products. So as a part of this law called Amara's Law, PFAS will be intentional use of PFAS will be prohibited in consumer products that are sold in Minnesota for several different categories. And so I emphasize the word intentional here because many people may not notice that there are non-intentional uses of PFAS because manufacturers might receive another component of their product from another supplier, and if they don't know that there's PFAS in that component, for example, a packaging material, they won't know that PFAS end up in their product. So on that note, at the federal level, there was recently an announcement that the EPA will be requiring reporting for manufacturers and reporters of PFAS to help improve transparency of what products that PFAS are actually present in. And also the US FDA recently announced that they will be no longer allowing production of food packaging that contains PFAS in the US. One thing that we could also do that has been suggested by scientists to improve regulation of PFAS would be to regulate them as a class rather than on a contaminant by contaminant basis. So you may have heard as sort of a trend today that as individual chemicals that are found to be hazardous and are banned, they tend to be replaced by chemicals that are structurally similar to have a similar function, and those chemicals can also end up to be harmful themselves. So if PFAS were regulated as a class, we could help avoid that sort of circular replacement of harmful chemicals with other harmful chemicals. Now, in terms of PFAS treatment, I mentioned that it's expensive. So one of those reasons is because the lower concentration that PFAS exists in a waste stream, the more expensive the treatment cost is per volume. And since PFAS, again, are so stable, the first step for treatment is oftentimes to first separate or concentrate the PFAS from the waste stream. Now, this can be expensive because it consumes materials. So adsorption with either activated carbon or ion exchange resins are well understood methods to remove PFAS from drinking water. So that's good news. We know how to do it. But it is just expensive because you need to replace the materials regularly. Reverse osmosis is another highly effective way to remove PFAS from water. However, it is especially expensive because it also consumes a substantial amount of energy. And following concentration of PFAS, now you have a concentrated waste stream on your hands that needs to be destroyed. So these are more of emerging types of treatment that are less well understood. However, in general, they require a large amount of energy and are also relatively expensive. So here I'm highlighting a study from, again, the team at St. Thomas and Barr, where they were evaluating the costs to treat PFAS in municipal wastewater, which I mentioned it has very dilute levels of PFAS. And what they found is that the cost for removing PFAS from wastewater can, in some cases, especially for smaller communities, exceed the cost of the median household income. And considering that the cost to treat PFAS in wastewater would likely have to go down to the consumer, this shows that it's potentially not a feasible solution to be treating PFAS in wastewater. So what we really need to do is try to prevent PFAS from getting there in the first place. And lastly, to end with what can we as normal people do? So one thing is to understand why PFAS have become such an urgent concern, and I hope that some of the things we've discussed today can help bring you to that understanding. Also, to keep things into perspective, you need to understand that exposure to PFAS at some level is essentially unavoidable. And most people are exposed at very low levels, and what we really need is regulatory action to help reduce the amount of PFAS that are produced and used in our products. You can also educate yourself. I've included several links here that you can follow to learn more about potential PFAS contamination sites in your area. And while you can't avoid PFAS exposure altogether, you can take practical steps to try to limit your exposure. I have a link to a MDH fact sheet, and I will emphasize to look for fish consumption advisories in your area. In terms of drinking water, if you're drinking city water, your city water is going to be held to those EPA standards, but you can also follow the MDH dashboard that I've shown here to see testing for PFAS and drinking water results in your area. If you have a well and you notice in one of these resources, that there's a potential contamination source nearby, you might want to consider finding some resources to have your water tested just to be safe. And lastly, supporting initiatives to eliminate non-essential uses would be important, and understanding that not all PFAS-free products will necessarily function the way that the other products with PFAS did. So one example is ski wax, which that might be very relevant to us northern Minnesotans. So if you're disappointed that your ski wax isn't as slippery as it used to be, I hope that you understand through this presentation today why it is so important for us to try to find a replacement. So lastly, just for some take-home messages, ultimately my goal today was that next time you see an article about PFAS in the news, you can read it without your head spinning, and also to drive home that the one of the main reasons that PFAS have become such an urgent concern and are different from other contaminants is that they're particularly persistent and they don't degrade in the environment, hence the term forever chemicals. But just because it's a problem doesn't mean that there's not a solution, and I hope that you've also seen that we're taking steps as a state and as a nation to address this problem, and that it's something worth working together to solve. So with that, I can acknowledge our team at the Natural Resources Research Institute. The sediment data that we showed was a lot from Quinn Whiting, a PhD student in our group, and then the results from the studies I've shown from the team at St. Thomas and Barr, I can credit Ali Ling and Andy McCabe, and also funding for the sediment work from the US EPA. And again, you can follow the link in the chat or this QR code to find a PDF of the presentation with links and resources. And with that, I can hand it back to Brian, and thank you so much for your attention.
Okay, thank you very much. That was wonderful. Thank you for your work, and also thank you for the presentation today. Sorry, I got mixed up on my script here. So let's go to the Q&A portion of today's program. Bill Granges is off today, and instead will be Hillary Sorensen of Minnesota Sea Grant. Hillary?
Thanks, Brian, and thanks, Bridget. That was a really awesome presentation. Really appreciate all of the information and resources you shared. So we do have some questions. I'll dive right in. First question is from Catherine. Does burning sludge in a city wastewater treatment plant add PFAS into the air in that community currently? Or does this have an effect from previous practices of wastewater treatment plant burning?
Yeah, so it's not completely understood what happens to PFAS during incineration, but in general, they're not necessarily completely destroyed down to, carbon and fluoride. They might be broken down to smaller PFAS components. So incineration in combination with treatment of the gas that is produced, is one approach to dispose of solid waste that's highly contaminated with PFAS. In terms of municipal sludge, the concentrations are, potentially lower than an activated carbon that has been accumulating PFAS for some time. But once PFAS enter the air, they can be transported much further, beyond just the community itself. So the PFAS that might enter the air from a smaller community could, end up miles away in a different location. So, I would say that, there might be other processes of release that might be more of a concern to that for smaller communities, such as their releases to groundwater and contaminating their drinking water.
Thank you. Okay, second question. This builds off of one of your final slides about what can people do, limiting our consumption of products that use PFAS. So how can we know if our personal products have PFAS so that we can phase them out? So are there code words and ingredients such as shampoos or cleaners that we can look for, that type of thing?
Yeah, the struggle with PFAS is one, there's so many of them. And also I mentioned the unintentional uses. For personal care products, they could be in the packaging and enter the product without necessarily being listed as an ingredient. And oftentimes they're not listed as ingredients because they're not a main ingredient. They're present at small amounts. So some products, so ski wax is just an example where it clearly says fluorinated ski wax, but that's just because that's known to be the fastest ski wax, so they advertise it. But those there are laws that have come into effect that should start to help remove some of these products from the market. So including Minnesota's PFAS ban, as well as the Toxic Substance Control Act ruling that the presence of PFAS needs to be reported by manufacturers and importers. So I guess the unfortunate answer is no. Generally, products that contain PFAS are not labeled, but there are laws coming into effect to hopefully remove those products that do intentionally contain PFAS from the supply chain.
Thank you. Anecdotally, there are some outdoor clothing companies that are starting to actually advertise that they do not use PFAS. So a couple of those, especially Kiddo outdoor rainproof, waterproof clothing is starting to do that.
Yeah, the voluntary disclosure. So, and yeah, if those products are available, you can help by choosing those products. So there's also some ski waxes that voluntarily don't use them as well.
Okay, this question kind of builds off of that. We have a lot of old ski wax. How do we properly dispose of it? And things like old waterproof clothing.
So I would say contact your local waste authority. So in Duluth, you would contact WLSSD. It depends on your community and what their programs are for disposal. So for clothing, they'd probably tell you to just put them in the landfill, honestly. I think for ski waxes, there may be they may actually have a different disposal method. But over time, the PFAS in your clothing are washed. So once you wash your clothing a certain amount of times, there's probably a lower amount of PFAS coming off of them, essentially. So.
Okay, this question is from Teresa. Are there any biological degradation methods available?
So that's an interesting question. So first of all, I explained that there are some polyfluorinated PFAS that essentially have portions of their molecules that aren't fully fluorinated. So those can be biodegraded in the environment. However, they essentially stop once they break down to the fully fluorinated version. There have been reports in the laboratory of biological microbial systems that can degrade PFAS in a way that actually degrades the perfluorinated PFAS called defluorination, so removing the fluorine from the carbon atom. And that's really the main challenge because that carbon-fluorine bond is so strong. However, those processes have not been shown to occur in the environment under environmentally relevant conditions. And if there is an advancement where that is identified, we would then need to figure out how to control it in a way. So currently, there are no viable bioremediation methods to defluorinate PFAS.
Got it. Thank you. Okay, this is coming back to one of your earlier topics, bioaccumulation. So how does the bioaccumulation of PFAS in fish compare to that of other contaminants like mercury and PCBs? And are current fish consumption advisories adequately addressing the combined risks of these contaminants?
That is a good question that I'm not necessarily the expert on, but I can answer it from the context of a chemist. And so I noted that PFAS are highly mobile in groundwater, which is a unique aspect from other bioaccumulative compounds. So because they're structurally different, they're not all hydrophobic. They have like that dual personality where one half the molecule is hydrophobic or one part of the molecule is hydrophobic and another part is hydrophilic. So that difference in chemical property and function very likely leads them to bioaccumulate in different ways than mercury or PCBs. So I don't have a definitive answer scientifically of, if they might bioaccumulate in different portions. But the advisories in terms of the lake-specific advisories for how many fish that can be consumed per month are definitely relevant. In terms of the advice for just cutting away the fat for PCBs, that may not necessarily be enough for PFAS because since they're structurally different, they might be accumulating in different portions of the fish.
Awesome. That was the second part of this question. So thank you for answering. Okay. Are PFAS only able to enter an organism through ingestion?
That is, I would say no. There are definitely other ways where you can be exposed to PFAS. Again, this is not necessarily my area of expertise, so I can't speak to skin exposure. But for example, through inhalation is definitely one other exposure route. So some PFAS are volatile, and for example, if you have your home water supply is contaminated with PFAS and some of them are volatile, you might inhale, be exposed through inhalation in the shower is one possibility. So no, not only ingestion, there's definitely other routes, and just inhalation is one example.
Got it. Okay. So there's another one about the uniqueness of PFAS. So given the unique properties of PFAS, how do they behave in lake ecosystems? Do these chemicals predominantly remain suspended in the water column, or do they tend to settle and accumulate in sediments? And how does this impact long-term contamination in aquatic environments?
I'm curious who's asking this question, so that's why
I think you can guess.
but yeah, so they definitely behave differently from other persistent bioaccumulative contaminants in lakes because they tend to accumulate at interfaces. So there's been some really interesting recent research about PFAS in sea foams. So since PFAS have that sort of dual personality, they tend to accumulate at interfaces between the water and the air. And in foams, there's a lot of surface area and interface between water and air. So PFAS can accumulate in those foams. Additionally, they are not necessarily evenly distributed in the water column, but some PFAS, for example, the very short chain PFAS, are more water soluble than others, so they can remain in the water column and aren't necessarily evenly distributed. And then the longer chain PFAS that I mentioned tend to be more bioaccumulative. Those tend to remain associated with sediments. And so, once PFAS get into a lake and get into the sediment, it's very unlikely that we're going to be able to treat them because they're just at such a low concentration and there's so much water and sediment in the lake. But eventually, if over time there's lower PFAS inputs into the lake, some of those longer chain ones potentially can settle out on sediments and then become somewhat isolated from the rest of the ecosystem as they become more buried. So,
okay. That
great
helps. And then just
question.
real quick, you've been talking a lot about the dual nature, the hydrophobic versus hydrophilic. Could you just explain that a little bit, like hydrophobic and hydrophilic?
Yeah, and I didn't want to get overly technical with the talk, so I appreciate the question. So you may already know that hydrophobic means afraid of water, and hydrophilic means loving water. So essentially, water itself is a series of small molecules that are all very attracted to each other. Because they have partial charges and positive and negative attract, right? So to include a contaminant that is not charged involves making a cavity in that water so that not charged compound can be present there. So that takes a lot of energy to sort of pull those water molecules apart. So the other side of the PFAS molecule is charged. So since water likes things that are charged, the charged end of the PFAS molecule is very happy to be surrounded by water molecules. So oftentimes as I say, the long chain, more hydrophobic PFAS, they'll want to be present somewhere where they're not completely surrounded by water, such as on a sediment molecule, or near a sediment particle on the surface. So,
got it. Thank you for that clarification. Okay, we have time for a few more here. What are some of the most cost-effective methods for small communities or private well owners to address PFAS in their water?
Yes, that's a great question. I'd say the most well-established and relatively cost-effective way is activated carbon. It's well understood, and we know that it works well. It's more effective for the long chain PFAS than the short chain PFAS for the reason that I just explained why they prefer to stick to sediments. However, the long chain PFAS are really the ones that are more bioaccumulative and tend to be more of a concern. So the activated carbon as well as ion exchange resins are another adsorption approach. Reverse osmosis is another available treatment for homes, and that's very effective for all PFAS, just can be more expensive due to the energy consumption. And those really are the main existing conventional technologies for PFAS treatment that are well understood enough to confidently be used to treat drinking water. And there's a ton of research available on emerging treatment approaches that are promising that haven't necessarily translated into practice, especially for technologies to destructively treat PFAS in highly concentrated wastes. And the main competitor is really activated carbon. Like, can these technologies, at least that are removing PFAS from the water, be cost effective and work as well as the existing conventional technologies?
Awesome. Thank you.
Yeah.
And then this is a related question. So there are a lot of disposable home water filter systems available. Are there any of these that are better for removing PFAS out of drinking water?
So in terms of actual single family household units, that's not something I'm especially familiar with. But in terms of drinking water, just a simple, pitcher with a filter, can potentially remove many of those longer chain PFAS. Also, keeping into perspective that, again, most people aren't going to need to worry about PFAS in their drinking water. And if you're drinking city water, there are new federal regulations that will help communities find resources to test their drinking water. So if you're receiving city water and your city is meeting those federal standards, it's not something that, me living in Duluth that I worry about. This is more about, and if you have a well, but you're not located near a potential contamination source locally, it's also probably not something that you necessarily need to worry about. There's really a small number of people who, might have a well and then there's a known contamination source that happens to be close enough, and the water is moving in the right direction that it might have caused it. So, the majority of us aren't going to need to worry about, setting up a home treatment system for our drinking water. But those few people who might be affected can use the resources I provided to see if there's any known contamination sources in their particular area, if they have a home, like a well, for their drinking water. So.
Thank you. And I'll just remind folks that there were some opportunities for getting your water tested on some of the resources that Bridget shared in her slides. So you can check those out. Well, thank you so much. I will pass things back over to Brian.
All right, guys. Thank you. Thanks, Hillary, and especially Dr. Bridget Ulrich. Thank you for your work. Make sure you register for our next Water Wisdom program coming up on November 7th to learn about low and no salt water softening and conditioning. If you would like to watch this program again or recommend it to your family, friends, or neighbors, a recording of today's talk will soon be on our website at tascawaters.org, along with all of our previous programs. To give us your feedback, please click on the survey link, which will be on screen at the end of today's program, which is now. You will also be getting an email evaluation form so you can choose how you'd like to respond. I'm Brian Whittemore for Itasca Waters. Thanks very much for being with us today.